Chapter 2 is Chemistry of Life. So this is chemistry basics and how they relate to biology. Basically, why we need chemistry to live and for our bodies to function. I apologize in advance. This is a very long unit, and there are a lot of slides in this lecture. So water is the majority of our body, right? Most of our body is made of water, so is most of the earth. Water is everywhere. It's in everything. It's essential for life everywhere. So most of the stuff in our bodies, even if it's not water, is something that is dissolved in water. So 50 to 75% of our body weight is water weight. And water is created by polar covalent bonds, and it's a V-shaped molecule. So actually, if you really look at a water molecule, it is V-shaped, but it looks like Mickey Mouse, his head and his ears. It's what a water molecule looks like. So water has different properties that support life. First, it's solvency. This is its ability to dissolve things. Cohesion, its ability to stick to itself. Adhesion, its ability to stick to other things. Chemical reactivity, its ability to participate in chemical reactions. And thermal stability, which is its ability to not heat up and lose heat really, really fast just with small temperature changes. All of these things are very, very important to water's ability to sustain life. So first, let's talk about polarity. So one of the really, really big properties of water is the fact that it is polar. And if you think about what polar means, people say things are polar opposites or the poles. We have the North and South poles. Those are magnetic parts of the earth, right? That's where the gravity changes and the core has pull on things. So polarity has to do with like magnetic attraction. So water is polar because in a water molecule, the charges of positive and negative are unbalanced. So it's like a scale where it's heavier on one side and the other, and one side slightly negative and one side is slightly positive. And if you think about things that are negative and positive, they attract to other things that are negative and positive. So in a water molecule, we have 2 hydrogens and 1 oxygen. The oxygen atom is much bigger than the hydrogen atom. So the oxygen is stronger. It has more protons, has more pulling power magnetically. So if I were to have an oxygen atom with all of its protons inside of it, it has 8, and a hydrogen atom with 1 proton inside of it, which one do you think would attract more negative to that positive protons? Well, if the oxygen has 8, it's going to attract 8 times more than that single hydrogen proton. So the oxygen pulls on the electrons a lot harder, pulling them closer to the center of the oxygen. So if you look at this model that looks like the upside down Mickey Mouse, you can see all the electrons in this bond are close to the hydrogen, are close to the oxygen and away from the hydrogen. There are no electrons on the outside of the hydrogen. So that means the negative charge leans towards the oxygen side. If the negative is leaning towards the oxygen side, the only thing left to lean the other way is the positive. So the hydrogens tend to be slightly positive and the oxygen tends to be slightly negative just because the distribution is not even. It's a neutral molecule, but the distribution of the charges is not even, making it slightly charged on either end. So this causes water molecules to easily attach to each other because there's a magnetic attraction between the positive and negative of different molecules. This positive and negative attraction between molecules forms hydrogen bonds. So these are little forces of attraction between a negative and a positively charged atom. In this case, it's the negatively charged oxygen attracting the positively charged hydrogen. We all know opposites attract. So if I have a negative oxygen, it's gonna attract that positive hydrogen. And it could attract multiple because oxygen is so much bigger than hydrogen. So these bonds are very weak and they can be easily broken, but they're very important because it makes water easily attach to itself. And they like to attach to themselves because when you have 2 magnets in your hand, they want to attract each other as long as they're opposites, right? It's hard to pull them apart, but it's easier to put them together. They like each other. They're attracted. So these water molecules always want to be together, and they always want to attract each other. And hydrogen bonds are specific to water. Remember that that's just water. Hydrogen bonds are just water. And it's the oxygen's negative charge attracting the hydrogen's positive charge. And then remember, these are neutral molecules. It's just unevenly balanced. More negative is on one end than on the other. It doesn't mean it is negatively charged. It's just slightly off with its balance. Because water is polar, it has the ability to dissolve many, many things. So solvency is the ability to dissolve things. So water is considered the universal solvent because it can dissolve more things than any other solvent that we have found in our planet. Metabolic reactions in our body, so anything that is metabolism, requires water. And there are hydrophilic substances that dissolve in water. These are polar substances, just like water. So polar likes polar. So water will dissolve anything that is also polar. And the term hydrophilic means water-loving. So anything that's hydrophilic is going to be polar, and it's going to love water, and it's going to dissolve really easily in it. Then we have hydrophobic substances, which if you think about what a phobia means, it means you don't like something. You're scared of it, you hate it, you don't want any part of it, right? So hydrophobic substances are non-polar substances that do not dissolve in water, such as fats and oils. Those kind of things are going to be hydrophobic. They're going to separate from water. So in order for something to be soluble in water, it has to be polarized or have a charge. And an example of this would be salt, sodium chloride. Sodium chloride is an ionic bond between sodium and chlorine because it's a metal and a nonmetal. It's an ionic compound that easily breaks apart in water because it is charged and it can dissolve. So if it's polarized or charged ionically, it will dissolve in water. And again, water dissolves more things than any other liquid or solvent on our planet. Continuing on with why polarity makes water what it is, water also has properties called adhesion and cohesion. So first we have adhesion. If you think of the word adhesion, it sounds like adhesive. Adhesive means sticky, right? Bandages, tape, things like that. So water is basically adhesive. It has a tendency to stick or cling to other things. So water adheres to membranes in the body easily just because it likes to stick to things. So if you're driving down the road and it's raining, you could see the water from the rain like running down your window. It doesn't just fly off. You know, it kind of like sticks to the window and rolls down. That's because adhesion. If you pour water on your table, it doesn't just like run away. It kind of like sticks a little bit. The drops can stick. That's because adhesion. Water is sticky. It likes to stick to things. And then water is also cohesive. And if you think of that prefix co again, it means like working together. Cohesion is when water works with water and sticks to itself. So cohesion is water likes other water. So if you pour water on top of water, it's going to stick to itself. If you have a drop of water and you put another drop of water on it, now you have one bigger drop of water because water will stick to water. And then if you put a few drops of water on a table and like stick your finger in it or a pencil, kind of drag it around slowly, the water will follow itself because water likes water. The reason it likes water is because of those hydrogen bonds caused by the polarity. So water will stick to itself, which is cohesion, and water will stick to other things, which is adhesion. So when you're looking at like water and bugs can run across it, it's because water is cohesive and it sticks to itself, which causes a surface tension. So there's a slight little film over the water of bonds that certain things are light enough or less dense than the water and can easily stay on top of it. So surface tension is caused by cohesion of water. It's when water builds on itself, attaches to itself, and adhesion, water sticks to everything else. The last property of water, but one of the most important ones, is its thermal stability. Water is very uniquely stable when we change the heat or the cold. If we change the temperature, water is really, really independent on maintaining its own temperature. So thermal stability is also referred to as a high specific heat. This is how much heat it requires to raise 1 gram of something by 1 degree Celsius. So the specific heat of water is really high, meaning if you have a lake and it's 80 degrees outside today and then it's 95 tomorrow, that lake is not going to increase 15 degrees because the temperature outside increased 15 degrees. The lake might only increase half a degree. It's because it takes a lot of heat to change the temperature of the water. So this is essential to life, because what would happen if it went up 15 degrees and that lake went up 15 degrees and now the water is all boiling and hot? What would happen? What would happen to our bodies if we were 98.6 degrees today but tomorrow had a fever and we're 103? What would happen if our blood our blood and all the water in our body heated up as much as our fever did? It would cause everything to fry. Like, we would be so hot on the inside. If that lake heated up, all the fish might die, all the plants might die. So it's really important for water to be able to independently maintain its temperature without the temperature outside having much impact on it. So thermal stability, or a high specific heat, is one of the biggest and most important properties that water can possess that is essential to life. Okay, so when we have water and we mix things into it or mix different things together, we come up with different types of mixtures. So mixtures are a complex mix of chemicals. So they can consist of substances that are physically blended but not chemically combined. Each substance retains its own chemical properties, but they are together. It can be separated, so the contents still remain themselves. So a mixture is like a bucket of Legos. They're all mixed together, but you can easily identify every color and every shape of Legos, and we could separate them back out if we wanted to. So a mixture, it's just a physical mix, but not any no chemical combination. So again, with the Lego example, if the Legos are still solid and they're just mixed, it's easy to fix. Now, if we melted them and chemically changed them into mush, they would all blend together, and then we probably wouldn't be able to get them separated. So a mixture, you can always re-separate it. It would be mixing vegetables together, mixing your Legos, things like that. So there are different types of mixtures. So mixtures of other substances in water are called solutions, colloids, and suspensions. So if we take anything else and mix it into water, it becomes one of those three things. So a solution is particles that are referred to as the solute, and the agent, the solvent. I remember the difference between the solute and the solvent as you have to go into the vent. So the solute goes into the solvent. So if we were mixing sugar and water, the solute would be the sugar because it's going into the vent, which is the solvent, which would be water. So you should always have more solvent than solute. The solute goes into the solvent. The solvent does the dissolving and is a liquid. And the solute can be any state of matter, solid, liquid, or gas. So if I'm making Kool-Aid, I'm going to have water as my solvent, right? Because that's what I'm putting the stuff into. And I would have more water than Kool-Aid, and I would have more water than sugar, because the water can't dissolve it if there's not more. It has to have more to do all of the dissolving. So the solvent is the dissolving agent, and the solute is the thing being dissolved. Okay, so now we have colloids. Colloids are mixtures of protein and water, and it's obviously something we find inside the body. So many can change from a liquid to a gel state, depending on where they are in the body and what they're doing in the body. These particles remain permanently mixed, and it doesn't settle. So a colloid will stay mixed even if you let it sit for 4 or 5 days. It's not going to separate. It's going to stay mixed. And usually they're cloudy. You can't see through them because whatever is mixed into the water, whatever proteins those are, they stay mixed and they constantly stay floating around suspended in that solution. A suspension is a solid mixed into a liquid. And if you think about what happens when you mix a solid and a liquid together, eventually, if you're not continuously mixing it, or if you don't remix it, the solid's going to float to the bottom because it weighs more, right? It's more dense and it's heavier. It will separate. So they usually look cloudy or opaque in appearance when they are mixed. But then when they settle, sometimes it gets clearer in the liquid part, but not in the solid part. A suspension, the most common example of a suspension is liquid medications that you get from the pharmacy. You have to always shake them up before you take them, because if you look at it, the medicine will be on the bottom and just liquid will be on the top. That's a suspension. And if you read the bottle, it'll say suspension right on it. So you need to shake them back up because they will settle. And then we have emulsions. So emulsion is one liquid inside of another. They usually do not mix well. One usually settles at the top, and it's usually because the things are not alike. Usually it's a polar and a non-polar thing. They don't really dissolve each other. So vinegar and oil, fat and breast milk, those are examples of emulsions. And if you ever have fresh milk, sometimes all of the cream will settle at the top because it hasn't been completely mixed. That's going to be an emulsion. It's going to separate. It's the fat separating from the milk. So here are some different examples of mixtures in relation to the human body. So when we draw labs, usually things come out in either a solution, a suspension, a colloid, or an emulsion. We use machines to spin blood to separate them. But some things settle on their own. So if you look at the first test tube, both diagrams, those are solutions. So if you look at A, it's blue. It's very, very evenly distributed, and you can completely see through it. That's a solution. So whatever was in there was completely dissolved. Okay, and then if you look at the drawing, you can see that all the particles are evenly spread out, and they're staying in that water. The next is a colloid. So a colloid looks a lot like a suspension in the fact that except for the fact that it's not see-through. It's not transparent. It's going to be opaque or cloudy. So you're not going to be able to see through it. And if you look at B over here in the real picture, you can't see through it. You can't see the lines behind it. It looks like milk in a tube. So the molecules or the particles, whatever it is, are evenly spread out in the liquid, but they are not dissolved. And then we have suspensions. So suspensions are either going to settle or stay like chunky. And if you look at these blood tubes, you can see how they are different. They have settled. So C, it's mixed. But then D is the same sample of blood, but you can see that it's separated. There's some yellow fluid on top, and then the blood is on bottom. So it was mixed. It was probably shaken or spun, and then now it has settled and separated. So a suspension will be nice and evenly distributed when you shake it or mix it. And then when you stop, it will separate. The solids will go to the bottom, and the liquids will stay on the top. The pH scale. So the pH scale is what we use to measure how acidic or how basic something is. So the pH scale goes from 0 to 14. There's nothing higher than 14. 14 is the highest. Right in the middle at 7 is neutral. Our bodies are right around 7. Water is 7. It's pretty neutral. So anything lower than 7 is an acid. Anything higher than 7 is a base. So the lower the number, the more acidic. The higher the number, the more basic something is. So we can measure the concentration of something a few different ways. So we can measure by volume, or how much liquid we have in a solution. So we can use the weight. So if we have IV saline, which is fluids that you pump into somebody's IV, if we have 8.5 grams of sodium chloride, which is table salt, per liter, that is a weight per volume. The weight is 8.5 grams, and the liter is volume. So 8.5 grams per liter is a weight per volume measurement of concentration. And remember, concentration is how much of something is in the solution. So we're measuring the concentration of sodium chloride in water. Milligrams per deciliters is really common in anatomy and biology. That's mainly what we measure blood and lab results in. You can measure the serum cholesterol, might be 200 milligrams per deciliter. That tells you how much cholesterol is in the body or in the sample of blood that was taken. We can use percentages. We can say there's 5% dextrose, which is a sugar, in 100 milliliters of solution. So we could say 5 grams in 100 milliliters, which would be by weight and volume. Or we could say 5%, which is percentage. So we can use any of these to measure the concentration of something, but electrolytes are usually measured in equivalents. So electrolytes are crucial for heart, nerve, and muscle function, and they are potassium, sodium, magnesium, those type of things. So let's talk about energy. So we have two different types of energy in our body. We have potential and kinetic. Potential energy is potential. It means that it's energy that we have, but we're not actually using it. So it has the potential to be used as energy, but we're not really using it yet. Kinetic energy is energy that we are actually using because we are moving. We're doing something. So if you're walking, you're using kinetic energy. That's kinetic energy. You're moving. If you look at this diagram of this girl holding the ball, the first one, she's holding the ball. The ball's not moving. But the ball has the potential to move if she lets go of it, right? The ball has the potential to move if she lets go of it because of gravity. So she has potential energy in this ball, even though it is not moving. It does have the potential. The next one, the ball is actually falling. So the ball is in the process of moving. It is kinetic energy because it is moving. Heat is kinetic energy, and it makes molecules move. And then there's electromagnetic energy, which is the kinetic energy of radiation. So radiation moves, and it's kinetic energy because it's moving, and it makes electromagnetic energy. So that's where magnetism comes from and why things are attracted to each other. And it's because little packets of radiation are moving around and they're making energy. Chemical reactions. So chemicals react with other chemicals for different things. We can make things, we can break things down, we can change things around. There's many different types of reactions, but it is a process which involves a covalent or ionic bond being broken or formed. So when something's bonding with something, it is a chemical reaction. When something is unbonding or the bond is being broken with something else, it is also a chemical reaction. So the chemical equation is the chemical formulas showing what is being put together or taken apart. So this picture is the chemical equation. It is showing that we have two H2 molecules, which is hydrogen, bonding with two O2 molecules of oxygen to make two water molecules. That is a chemical reaction. It's showing this that we're having hydrogen added to oxygen, and it makes water. So when we're looking at the chemical equation, on the left side, you're always going to have your reactants, which is what's going into your equation. And on the right side, you're going to have your products. And then remember, when you have products, it's something that was being produced, right? So it's always going to be on the right side of the equation, what comes out of the chemical reaction, what is produced in the reaction. And then chemical reactivity refers to the ability for something to participate in a chemical reaction. So something that is more chemically reactive is more likely to bond or unbond with something. It's more likely to participate in a reaction. Something that is not chemically reactive is not going to participate in a reaction. So there's different types of chemical reactions. First, we have a decomposition reaction. This one's pretty simple because if you think about what decomposition means, it means to break down. So in a decomp reaction, a large molecule breaks down into two or more smaller molecules. So in this example, we have A and B bonded together. They break down and separate to form A and B. So we use these in our body to break down food and nutrients. When we eat food, it has to be broken down. It doesn't go into our stomach and stay, the same as it was. We have to break it down with enzymes and chemicals. So that is decomposition. In cellular respiration, we break down glucose to make energy. And then in aerobic respiration, we also break down glucose to make energy. The next type of chemical reaction is a synthesis reaction. The word synthesis means to build, make, or create. So anytime we're synthesizing something, we're making something. So a synthesis reaction is opposite of a decomp reaction. So in a synthesis reaction, you're going to add two or more things together to make a bigger molecule. So in this situation, we have A plus B yields bonded AB. So examples of this are protein synthesis, which is when our body makes proteins. We have to build them up and make them. Or when we're growing, we have to make more bones, we have to make more muscles, we have to make more tissues. All these things occur through synthesis reactions from different chemicals, different elements, all these kinds of things. So not only can we take things apart and put things together with chemical reactions, we can switch things around. So when things are switched around during a chemical reaction, it's called an exchange reaction. So it's when you have a set of reactants that go in paired a certain way and come out paired differently. So in this chemical reaction, we have AB plus CD. They make AD and BC. They came out with different partners. So this is an exchange reaction because things are being exchanged. So some of these reactions that occur in our body are stomach acid and sodium bicarb. Those combine to make sodium chloride and a bicarbonate. This helps break things down. So something is exchanged, it's twisted around, it's changed. I like to think about this as, you have a date and you have a friend that has a date and you guys go to a dance or prom or whatever it is and you trade dates and come home with a different date. It's just swapping. Everything is just changing around. So since we talked about the 3 different types of reactions, from this picture, what do you think is occurring? Like, what type of reaction would this be? You have these single amino acids, and then you have this chain of a protein molecule. So you start with single things, and then you have them connected together. So this would obviously be a synthesis reaction because we're starting smaller and building up to bigger. What type of reaction would this be? You have CD and AB, and then they go into this chemical reaction and they come out as Ca and Db. So they're not breaking down, they're not growing, but they're switching around. So this would be an exchange reaction. And lastly, this reaction starts with something that's all attached, and then it separates apart. So what kind of reaction takes something that's solid and breaks it down to smaller pieces? That would be a decomposition reaction. It's breaking it down. Okay, so we have some reactions that are reversible, meaning they can go both ways. So a reversible reaction can go in either direction. So you can have products making reactants or reactants making products. Usually they go back and forth simultaneously. These reactions are shown with a double arrow. So if you look at this one, the arrows are going both directions. So one example of this in our body is the binding and unbinding of oxygen in our blood. So we breathe in, oxygen enters our lungs. Somehow it has to get in our blood. So way deep down in the very bottom of the branches of our lungs, we have these little things called alveolar sacs. This is where the actual oxygen exchange takes place. So within those sacs, we have blood. The blood has hemoglobin on it, which loves to bind with oxygen. So the blood travels through there. The oxygen's hanging out waiting. The blood will pick up the oxygen, drop off CO2 at the same time, and then move on its way. It'll go into the heart, do the same thing in there, do its switcheroo, give the heart its oxygen, go through the body, give the tissues its oxygen, give the brain its oxygen, do whatever it does, and then it'll go back to the lungs again, pick up more oxygen, drop off more CO2. And these things are being done both directions. It's picking up and dropping off all the time, oxygen and CO2, back and forth, back and forth. So this is a reversible reaction. It could go either way at any time. Another type of chemical reaction that occurs in our body frequently are redox reactions. So these are reduction and oxidation reactions. And it's called redox because the reduction and the oxidation happens at the same time. So in a redox reaction, one thing is oxidized and the other thing is reduced. So electrons are transferred from one thing to the next, and they usually are transferred as hydrogen atoms. And a redox reaction is really common in ATP or energy production. That's the most common one that occurs in our body. Okay, so oxidation is when a molecule gives up electrons and releases energy. It's oxidized because it loses electrons. The oxidizing agent is the thing that took the electrons from it. So in this situation, A loses its electron, so it becomes oxidized. B took the electron, so B is the oxidizing agent. Usually oxygen is the one that takes the electrons, which is why it's called oxidation. Usually oxygen is the one that's doing the oxidizing and it's taking the electrons away. Reduction. Reduction is any chemical reaction in which a molecule gains electrons. So a molecule is reduced when it accepts electrons. And it's called reduced because remember, electrons are negative. So if something has a 0 charge and it takes 1 negative electron, now it has been reduced down to a -1 charge. So it's called reduced because it's gaining a negatively charged electron. So then the reducing agent is the thing that is giving the electrons away. So A is giving its electrons away. It is the reducing agent. And B is the oxidizing agent. Reaction rates. Exactly what it sounds like, the rate of a chemical reaction. So reactions occur when molecules are running into each other with enough force to change the direction of something. So one molecule crashes into another and then it changes the path of that molecule. That's when a reaction occurs. So you can speed up reaction rates with different things. Some ways to speed them up are adding more reactants. So if I'm cutting wood, like say I have a wood chipper and I'm putting trees in there and I'm cutting it and cutting it and cutting it. If I don't have any trees to cut, am I cutting fast? Am I cutting a lot? No. But if I add a bunch of trees, I can cut more, right? So if we add reactants, which are the things that go into the equation, we can speed up the reaction. If we have readily available things to react, we can make the reactions happen faster. We can increase the temperature. When you increase the temperature, molecules move faster. And if we need molecules to run into each other or collide to make a reaction happen, if we make them move faster, they're more likely to hit things harder, quicker, and more frequently, right? So if we raise the temperature, we're going to speed up the rate of a reaction. And then we can use a catalyst. A catalyst is anything that increases the rate of a reaction. Typically, in the human body, enzymes are catalysts. So we use enzymes to bind to the reactants and hold them in either places or states where they need to be so that reactions can happen easier and faster. So when we use catalysts or enzymes to do these reactions, they're not changed or affected by the reaction at all. So an enzyme can do 1 million reactions in a row and it never gets affected by it. Its job is literally make the reaction happen, move on to the next thing, make the reaction happen. They're never changed or affected by the actual process of the reaction happening.